Hello there, welcome to my physics project. Today I'm going to be demonstrating 4 different types of air pressure demonstrations. My project consisted of a lot of non-complex items. For the height pressure demonstration, I had to collect cans from my house and bring them into class. After doing this, I had to go and collect vinyl tubing from Home Depot. I also had to purchase rubber sheets that will be shown in the next video. Fill 1 can of water full. After filling your can full of water, you're going to want to put a rubber sheet over the can and put the tubing through the rubber sheet into the can. You then take the remaining tubing and throw it out a window. While doing this, you turn the can upside down, maximizing no air to get inside the can. If air gets inside the can, your demonstration will be ruined. As seen in the demonstration about now, the can starts to crush because there's no air being allowed into the water. This allows the can to be crushed and your demonstration to be complete. Atmospheric pressure is the force exerted by the weight of the air in the atmosphere. At sea level, this pressure is around 1 atmosphere, or around 101,325 pascals. While right side up, the water pressure from inside the can pushes outward onto the can and the lid. When you turn the can upside down, the water's weight now pushes against the lid from the opposite side. The key factor here is not the water pushing down, but rather what happens to the air pressure inside the can. Now remember, atmospheric pressure is acting on all sides of the can from the outside of the can. When the water escapes from the can, from the tubing to outside the window, this heavily decreases the pressure inside the can. With the internal pressure being reduced, the external pressure, atmospheric pressure, is greater than that inside the can. Because of this causes the can to collapse and crush. This creates a vacuum, which in turn is what I just described before. Also, the greater height of the bottle from the end of the tube leads to lower pressure in the bottle. This leads to a quicker crushing of the can. Next up, the temperature can implosion demonstration. I first started filling up a can with ice-cold water. I will then use this ice-cold water later in my demonstration. After filling the can with about a tablespoon of water, I placed the can on top of a hot plate. I waited until I saw steam coming from out of the can. Once I saw steam, I knew my can was ready. But now, the most important part of it all is to take crucible tongs, mine were acquired by Mr. Padron, and in one swift motion, turn over the can and pour the water into the ice-cold water. If done correctly, with no air in between the can and the water, the can should implode.
Nice.
This right here is a good example of me doing it incorrectly. I didn't do it in a swift motion, and this led to the can not being imploded and my classmates being very upset with me. Now the physics behind this can be explained by this. When the water inside the can is heated up, the air is as well. And then, once you turn the can upside down into the cold water, all this air contracts very quickly. This change in air pressure, especially the low pressure, is what causes the exterior atmospheric pressure to crush the can. The high pressure, the atmospheric pressure, wants to get to the low pressure inside the can, and its only way of doing that is through the sides of the can, due to the top of the can being closed by the water. All you will need for this demonstration is 2 beds of nails and an inflated balloon. You're going to want to inflate the balloon to a certain extent, but not too inflated. If done correctly and pushed at the same time, the balloon will not pop.
Stay recording.
This is another demonstration of me popping the balloon.
Hey, DK,
I just wanted to add this in. It's a little funny and just shows the enjoyment of my classmates.
All right, this is me and DK. DK is not really involved in this.
But he's here now. Say hi,
But
DK.
I just blew this balloon up with air, and we're going to be testing the bed of nails theory, where because of the proximity of the nails and the sharpness of the nails all at the same time. When you place it together, it should not pop until a certain time. But as you can see, it went pretty far without popping. Yeah.
So as I was kind of describing in that past video, the physics behind this goes as follows. When you put a balloon on one nail, it easily punctures and pops. But in this case, because there are so many nails and because of the sharpness and the proximity of each other to one another, it causes the balloon to not pop. This is because the total force is divided upon each point, reducing the stress. The equation P equals F over A shows that pressure is reliant on the force being over A, which A in this case is the nails, and more nails equals less pressure. Number 4 is the water bottle pressure demonstration, and I demonstrate in the video how it happens.
The water bottle atmospheric pressure demo, and as you can see, there's no leaks in the water bottle other than there, just a little. But the reason that there's no leaks, there is a hole in here somewhere. And the reason that it doesn't leak is because the pressure inside the water bottle is lower than the outside, and the air from the external pressure wants to get in through that little hole, and that's why it's pushing and it's not coming out. So as you can kind of see from the top right here, it's getting a little lower because of the low pressure, and the air is squeezing in on it. And if I loosen this cap, it'll start spraying because the air now has access to the inside because the higher pressure wants to go to the lower pressure, pushing out that water. But as soon as I close this cap, it goes back to the closed container, and the low pressure is the same, or is lower than the high pressure, and it wants to get through that hole, causing the bottle to leak.
So, as I was explaining in my video, in case it was in any way confusing, the reason the water does not leak when the cap is sealed is because the pressure of the atmosphere wants to get inside of the water bottle, and when sealed, its only way is through that hole, creating almost a seal at the hole. However, when the cap is open, the pressure from the atmosphere now goes through the top of the water bottle, pushing out the water through the hole.